Hello everyone! This is the last video of my playlist about the preparation of aromatic and heteroaromatic nitriles. In this video we'll have a look at the conversion of other benzoic acid derivatives into nitriles. In other words, we won't change the degree of oxidation of the starting material. The most relevant starting materials are benzotrihalides, benzoic acids and benzamides. A few examples of the direct conversion of carboxylic esters into nitriles have also been reported, but this reaction is difficult to perform and not as convenient as other strategies. Trichloromethylarenes are readily available by radical chlorination of toluenes. Treatment with ammonium chloride and some catalyst at high temperature can cleanly yield nitriles, as in this example. Here, 10% of the corresponding benzoic acid was used as catalyst. Because 4 equivalents of hydrogen chloride are formed, the reaction conditions are strongly acidic and not compatible with acid-sensitive starting materials. All kinds of nucleophiles should be avoided because these could add to the newly formed nitrile. Also, copper oxide can catalyze this transformation, as in this example. The starting material can be obtained by exhaustive radical chlorination of 3-methylpyridine. Trihalomethyl groups become more reactive when elimination of halide can occur by vinylogous beta-elimination. This would be the case in 2 or 4 trihalomethyl phenols and anilines, or trihalomethyl imidazoles, as in this example. Here, a trifluoromethyl group was converted into a cyano group by stirring with dilute aqueous ammonia at room temperature for 4 days. The reaction probably proceeded by elimination and formation of a fulvene-like anti-aromatic intermediate, as shown here. Interestingly, despite the large excess of water, no significant amount of amide or carboxylic acid was formed. This is another example of the conversion of a trifluoromethyl into a cyano group. Once the aniline was formed by aromatic nucleophilic substitution, vinylogous elimination of hydrogen fluoride initiated this transformation, like in the previous example. Trihalomethylarenes with ortho or para-alkyl groups containing benzylic hydrogen are also easier to convert into nitriles than unsubstituted trihalomethylarenes. Here, vinylogous elimination was induced by metallation of the benzylic position with potassium hexamethyl disalicide, which also served as nitrogen source. Also, carboxylic acids can be directly converted into nitriles. One strategy is treatment with an excess of another nitrile, conveniently acetonitrile, and some catalyst at high temperature, as in this example. This reaction is assumed to proceed by initial acid-catalyzed addition of the acid to the nitrile, followed by some rearrangements, as sketched here. Aluminum chloride could also be used as catalyst, but indium chloride seemed to be more effective. Alternatively, ammonium carboxylates can just be heated in the presence of ammonia and a catalyst, as in these examples. High temperatures are required though, and not all acids are thermally sufficiently stable under such conditions. More reactive than ammonium carboxylates are acyl chlorides. When these are heated with certain nitrogen donors, acceptable yields of nitriles may result already at moderately high temperature. In this example, the nitrogen source was sulfamide, which was converted into sulfamic acid during the reaction. Amides are the most common acid derivative used as precursors for nitriles. I've listed here some of the more practical dehydrating reagents. Particularly convenient are acetic anhydride and thionyl chloride. One problem of this strategy is that amides are not always readily available. Ammonia is a poor nucleophile, and mixing some activated carboxylic acid derivative with an excess of concentrated aqueous ammonia often causes extensive hydrolysis. Thus, this strategy only makes sense if the starting amide is readily available at a reasonable cost. In this example, a benzonitrile was prepared in high yield from a substituted benzamide, just by refluxing with an excess of acetic anhydride. No transesterification of the ester occurred. Phthalic anhydride can be readily converted into a monoamide by treatment with anhydrous ammonia, as shown here. Treatment of this amide with an excess of acetic anhydride in pyridine at room temperature gave, after acidification, a good yield of 2-cyanobenzoic acid. Another inexpensive dehydrating reagent is cyanuric chloride, the trimer of cyanogen chloride. Here, a benzamide was converted into a nitrile with this reagent in DMF at 0 degrees Celsius in only 40 minutes. Half an equivalent of cyanuric chloride was enough, and the terz-butyl carbamate remained unchanged. Benzamides substituted with electron-withdrawing groups are more difficult to dehydrate. In this example, 4-nitrobenzonitrile could be prepared from the benzamide in high yield, again by treatment with cyanuric chloride and DMF at room temperature. If the starting benzamide contains unprotected hydroxy groups, these will also react with most dehydrating reagents. Thus, a reagent should be chosen which enables an easy regeneration of these hydroxy groups. Here, salicylamide was dehydrated by treatment with thionyl chloride in hot chlorobenzene, and the phenol was obtained directly, by concentration of the reaction mixture, without any aqueous workup. Also, unprotected amino groups can react with most dehydrating agents, and it can be difficult to predict correctly if a given amino group will react faster than an amide. In this example, despite the excess of tosyl chloride, no sulfonamide, but only the expected aminonitrile was obtained. When thioethers, trivalent phosphines or triaryl phosphides are mixed with chlorine or bromine, highly reactive intermediates result that can be used as dehydrating reagents. Here, the product from bromine and dimethyl sulfide effectively converted 4-nitrobenzamide into the nitrile. The reaction was conducted in acetonitrile, and as byproducts DMSO and hydrogen bromide were formed. Phosphorus oxychloride is also suitable for dehydrating amides containing unprotected amino groups, but less so for amides containing free hydroxy groups. The latter tend to form phosphates which are difficult to hydrolyze. In this example, a cinnamic amide with a primary aromatic amino group was dehydrated with a large excess of phosphorus oxychloride at room temperature. Here, a substituted nicotinamide was dehydrated with a slight excess of phosphorus oxychloride. The unprotected aromatic hydroxy group was sufficiently deactivated by the pyridine ring and the nitro group and reacted more slowly with the dehydrating reagent than the aminocarbonyl group. With a larger excess of phosphorus oxychloride and at a higher temperature, 2 hydroxypyridines are usually converted into 2 chloropyridines, but this did not occur here. 2-hydroxybenzonitrile is required for the manufacture of the fungicide azoxystrobin, and its preparation from salicylamide has therefore been thoroughly investigated. One problem of the synthesis is the easy trimerization of 2-hydroxybenzonitrile to a triazine. Optimized procedures include the dehydration with thionyl chloride, which I already showed you, and this gas phase acid-catalyzed dehydration. Even N-alkyl amides can sometimes be dehydrated to N-alkyl nitroleum cations, which upon dealkylation yield nitriles and alkyl halides. Here, for instance, N-isopropyl-toluamide was dehydrated and dealkylated to the nitrile by treatment with a mixture of bromine and triphenyl phosphide. Also, hydroxamic acids can be converted into nitriles, as shown here. This requires a reductive NO bond cleavage, which was achieved in this instance with phosphorus tribromide. Hydroxamic acids are sometimes easier to prepare than amides because hydroxylamine is a stronger nucleophile than ammonia. Esters, for instance, often react cleanly with hydroxylamine, but not with ammonia. Benzoic esters are less suitable starting materials for the preparation of benzonitriles. Few examples have been reported, and expensive reagents are often required. In this example, the reagent was prepared from anhydrous ammonia and the highly pyrophoric trimethyl aluminum. Because of the many types of chemistry discussed in this video, I cannot go through all potential side reactions. Several of the strategies presented here require high reaction temperatures, what can cause decarboxylation of certain benzoic or heteroaromatic acid derivatives. Then, some nitriles or synthetic precursors to nitriles readily form triacenes, especially upon heating in the presence of acids. In the example shown here, an unsymmetric triacene was prepared from benzonitrile and 4-bromobenzoyl chloride. But more problematic are symmetric triacenes formed by trimerization of a given target nitrile. These triacenes have almost identical NMR spectra and give the same elemental analysis as their parent nitriles, and care must be taken to distinguish between the two. Here are some more examples of the conversion of benzoic acid derivatives into nitriles. These references can also be found in the description of this video. I have not included procedures based on mixtures of iodine with ammonia or ammonium salts because these are way too dangerous and should not be tested, not even on a small scale. So that's it. I hope you found this overview useful and stay tuned for more videos on the synthesis of specific organic compound classes.